Now I'm going to talk about this one. So this is the exciting moment at which we get to do something with a finite element basis function that we can actually see. So if you have some random function of space, so a thing which takes in points and gives you values back, think of some trig function as a good example, some sort of function. And you want to interpolate that function into a finite element space. So you want to get a representation of an approximation of that function in a finite element space. One of the ways you can do that is by interpolation. So you can take the finite element space which in some sense coincides as well as possible with the other space. That's really useful for doing things like building the forcing functions that turn up on the right-hand sides of PDEs. So how do you do that? Well, this is where the fact that we have a nodal basis comes into play. Because as we've met before, finite element functions look like this. So if you are a function in a finite element space, then you, what is true is if that function is hit with one of the nodes of the finite element space, it pulls out the corresponding coefficient. Why is that true? Well, it's true because the nodes, if you remember, are orthogonal to the basis functions. So when I substitute into this expression that this is equal to the sum of fi phi I, or fj phi j to disambiguate the indices, then all the ones which this doesn't match will evaluate to 0, and exactly the one that it does match will evaluate to 1, so you just get left out with the fi out. So it pulls out that one value. If we generalize that slightly, if I take a more general function that is defined over my domain, and I evaluate the nodes in turn onto that function, what I get are the coefficients which interpolate that function into my finite element space. And as a practical matter, in our case, we only care about point evaluation nodes. So actually, if you remember when we wrote down our finite element space, in the slot for nodes, we just put a list of points. And so all this has to do is evaluate a random function that comes in at that list of points. Simples. The interpolate method takes in a function. It's attached to the finite element. It's a method of the finite element, so it already knows about what the nodes are. You evaluate the function at the nodes, you return that vector. There is a script, and if your virtual env is active, then you can just type this on the bash command line because the script is in the directory that it knows about, which uses this and your definitions of basis functions further up and plots the effect of interpolating a function into finite element space. So you can actually see what happens. So at long last, there's something to take home.